Okay, we'll look at a couple of applications of friction with the half-Atwood setup from forces and acceleration. So here we're looking for if there's friction acting between the cart and the table, and like say we took off the wheels, what would the minimum value of the coefficient of static friction be to have it sit still? Okay, so the bigger that value of the static friction coefficient is, the bigger the friction force could possibly be, so we could hold up, potentially a pretty heavy mass. But if we sneak that down and down and down and get it smaller and smaller, at some point the friction is going to break and it's going to start to slide. So our situation, again, little m, big M, there's a coefficient of static friction between the two surfaces. That's what we're trying to find. We'll assume that we know big M and little m. And this thing is just sitting at rest. Okay, so we'll draw free body diagrams for big M. There's a normal up from the table. It's also interacting with the earth, big mg. It's being pulled to the right by the rope, so a tension, and it's not sliding because there is static friction. So I'm going to call that F sub s. I'm going to call right and up positive. Okay, for little m, it has a weight that's smaller than big M's weight, and it's pulled up by the tension, so those two tension forces should be the same size here. Because I chose right as positive here, I'm going to choose down as positive. It's not accelerating, so it's not going to impact our calculations, but you need to think about it all the time. It's just good practice. Alright, so Fnets. So Fnet for the cart in the x, I have t to the right and F sub s to the left, and this is balanced because the system is just remaining there at constant velocity. The velocity happens to be 0. In the y dimension for the cart, I have normal force up, mg down. And Fnet for the hanging mass, I have mg down, which is going to be positive for me, and t up, and again, it's balanced. So what I'm saying is that because the static friction coefficient is at its minimum, that means that I'm getting everything I can get out of my static friction force. Even though it's not a super lot, I'm getting everything I can get out of it. So I'm justified in saying that F sub s is equal to mu sub s times n. I can only do that if I know my static friction force is maxed out. So using this equation here, I can say that t is the same as mu sub s n. In this equation, I see that n is big mg, so I can sub in there. So I'm looking for mu sub s. I still need to get rid of t. Over here, I can see that t is equal to little mg. So mu sub s mg equals little mg. I can lose the g's. So mu sub s is little m over big M. That's the minimum size that that friction coefficient needs to be in order for this to work. So let's think about the functional dependencies here. In order for little m, if little m gets bigger, if I'm hanging a bigger mass off of it, then I need a bigger static friction coefficient to be able to handle that. And if the block on the table is bigger, I need a smaller one. So that all makes sense.